Hello everyone. Finally, we are into our last sections of chapter 8. In this last sections, we would like to show you how to graph a log functions. Okay? Before we start to graph the log functions, I want all of you to think about the relationship between the log function and the exponential function. You know how when we first started with this chapter 8 units, we showed you how from an exponential form we can change it to a log form, and then from a log form we go back to the exponential form. So that means they are closely related to each other. I guess by now you should know the exponential functions, in fact, the inverse of the exponential function is the log functions, okay, or vice versa. So they are the inverse of each other, all right? So let's look at the exponential form, okay? Y is equal to b to the power of x. And we already know that in the exponential functions, depends on the base. So there are two different type of a graph for the exponential functions. If the base is greater than 1, then we have that's what we call the exponential growth. So the graph of the exponential growth is rising up rapidly from left to right with the horizontal asymptotes. Okay, so some of the properties that we already studied from before, that in any of the exponential functions, we know that there is a horizontal asymptotes. That means that the one of the tail will never cross the x-axis. So we need to label the equation of the horizontal asymptotes and has the equation of y equal to 0. And another important properties of the exponential function is that it always has the y-intercept at 0, 1, right there. Okay, so that is when the base is greater than 1. Now, when you have the base that is in between 0 and 1, okay, which is a fractions, then in a case like that, then you will, instead of rising up rapidly, you will dropping it rapidly, okay, like this one over here. So this graph here is also y is equal to b to the x, but it's just that this one here is the exponential decay. Exponential decay is drop exponentially, and this one over here is rise exponentially. Okay, now so both of this, whether you have the base greater than 1 or it's in between 0 and 1, they both get the same y-intercept, because when the x is equal to 0, you basically turn everything into a 1. So in exponential growth or exponential decay, they all cross the y-axis at 0, 1, okay? And they both has a horizontal asymptotes at y equal to 0, okay? Same for the exponential growth or the exponential decay. Now, in order to graph the inverse of that, which is the log bx, okay, with the same base, okay, but the log bx, then how do we do that? Well, do we do a table values? Well, I guess it's just too time consuming, and especially when it's not easy to get the different base from the calculator. The calculator only has the base of 10, right? So if this is the base is not 10, then you will have a lot of trouble getting the values by creating a table of values for that. So, but by knowing the relationship between the inverse of each of the function, all we have to do is that we just interchange every key points, the x with the y. So the y becomes the x and the x becomes the y. So by doing that, I'm going to show you now ahead of time, okay, that since the log function is the inverse of the exponential function, so the log functions must be the reflections of the exponential function across this diagonal line, y equal to x. Remember, all the inverse, they are basically is a reflection that across from this y equal to x line. Okay, so The exponential function is the same thing. So this is my exponential functions. If this is my mirror line, so when I reflect this over, then this one will be the log functions of that. And since I have a simple, quick ways of looking at that is when you have a y-intercept of 0 and 1 from the exponential. So that means I must have the x-intercept at 1, 0. So instead of having a 0, 1, now I have a 1, 0 down here, okay? So these 2 points, they are the reflections of each other. And so does every single point that's on here. Every single point here get reflect across this line, and that's how you will see this log functions over here, okay? So what is in red, those are the special properties of the log function, and what is in the blue color, those are the important properties of the exponential function. So in the exponential, when we have the horizontal asymptotes at y equal to 0, so after you get reflected, okay, across this line, now you have the vertical asymptote instead. So no more horizontal asymptote for the log functions, but instead now we have the vertical asymptotes at x equal to 0. We labeled it down here, okay? Now, this will happen the same thing when the base is a fraction, when it's an exponential decay like that, okay? When you have a mirror line y equal to x, so every single point over here get reflect to the other side. But now this, the log functions for this one, it will approaching the y-axis up here and not down there anymore. So this one here basically is the y equal to log bx. But it's just that b is in between 0 and 1. So that's why it looks different than the first one that we see over here. Okay? So basically you will have a vertical asymptote at x equal to 0. You will have a x-intercept at 1, 0, same as this one here. Okay? So this is the look of the log functions, okay, when we have the base of b in 2 different cases. Okay, so let's work on the actual example, so you get to see how do we graph that. Okay, how do we graph that? Now, example number 2, when we have an exponential functions y is equal to 10 to the power of x. Okay, so because this one has the base of 10, then I know that right away is inverse. It must be the y equal to log x, okay? The 10, because the base is 10, then I don't need to write the 10 down here, okay? But if this is not 10, then I will need to write the base right beside the log, okay? But let's do the simple one first. Now, for the y equal to 10 to the power of x, if I want to graph this, I just need to do a table values like with a couple of points, and I know that, just like this one here, I know that the y, the horizontal asymptote is going to be at y equal to 0, right? Because this is one of the important properties. And if I sub in 0 over here, I get a 1. So I got a y-intercept at 0, 1. And if this is a 1, then I get a 10, okay? And if this is a 2, then I get 100. So number will get higher and higher because this is the exponential. Or you can give yourself like a negative, okay, doesn't matter. But if you put in a -1, and so the y is going to be equal to 1 over 10, so which is a 0.1, okay, which is a very small number anyway. But regardless, and we don't need to have more than 3 key points really. Even 2, plus the horizontal asymptotes, I should be able to graph this, no problem, okay? So on the graph, so let me just graph this. If I have a graph here, and I can basically know that my point is going to be like 1 here. And if this is a -1, I'll have something that's really, really tiny over here. And I know that this is going to be crossing the y-intercept of 1, and I can just go up like this. So if this is a 1 over here, then I know that this point here will be approximately equal to 10. Okay, so that's okay. So this graph here will be very similar to what I did above. Okay, I only need to know that it crossed the y-axis at 1, and then the rest is really not important because I know that this is going to be my horizontal asymptotes. So y equal to 0 is going to be my horizontal asymptote here. Now, in order to do the inverse, all you have to do is to make sure that you interchange the x and the y from the exponential form, because that will be the easier ways to do it instead of you trying to calculate from your calculator. So all I need to do is I interchange. So instead of 0, 1, now I have a 1 and a 0 and a 10. It will be a 1 and 100 here. That would be a 2. And if I have a 1 over 10, then I will have a negative 1. Okay? So I know that my others, the inverse of that one is going to be a 1 and a 0. It will be crossing this point here. Okay? And because I have a vertical asymptote now, this is called x equal to 0. And I know that my point is going to be like this, approaching and go like this. Well, I don't need to show my reflection line, which is the y equal to x, but you can see like all the way come to here. Like if this is a 10, then I know that I have a point at 1. Sorry, maybe I should adjust this one a little bit, okay, because then if this is a 10, then I will have a point at 1, something like this. Okay, so this will be my y equal to log x. And this one here will be my y equal to 10 to the power of x. Okay, so this is a very simple example to show you how quickly that you can come up with the exponential graph, okay, with 2 to 3 key points, but plus the horizontal asymptote. You can quickly draw that. And it's so much easier to form the table values for the exponential, okay? And then all you do is the interchange the x and the y coordinates, and then you will get your log x, okay, for this one here. So let's look at another example where the base is going to be a little different, okay? Now, in this question here, I have y equal to log 2x. So that means I'm giving you the log equation, but you need to graph both the original and its inverse. Well, if log 2x is the original, then its inverse must be y equal to, well, if the base is 2, then this one has to be 2 to the power of x. Okay, so this is how you can tell the inverse of each other by looking at the base. So this basically is going to be the log 2x, then the inverse will be a y equal to 2 to the x. Or same thing, if I'm giving you y is equal to 2 to the x, just like y is equal to 10 to the power of x, then you know that the inverse will be the log form, the log x, but with that same base. So if this is 2, then the base must be 2. Okay? Now, if I want to create this table values for the log, that would be difficult, like I have told you before. So instead of doing that, I always do the table values for the exponential form. Okay? So if this one is the y is equal to 2x, so that means if I put in a 0, then I'll get 1. Okay? Anytime when the exponent is 0, your answer is going to be turned into 1. If this is a 1, then you get a 2. And if this is a 2, then you get a 4. Okay? And so on and so forth. But I don't need to have any more points because I know that y equal to 2 to the power of x also has a horizontal asymptote at y equal to 0. Okay? And then for the log, which is the inverse of that, all you have to do is to interchange the x and the y. So now instead of a 0, 1, now I should have a 1 and a 0, okay? And this will be a 2 and a 1 and a 4 and a 2, okay? And for this one, I know that I will have a vertical asymptote at x equal to 0. So a vertical asymptote, x is equal to 0, okay? So if you want to do this graph quickly, okay, down here, and you know that I will always do my exponential one first. So when I get a 0 and 1, I get here. And I also have my horizontal asymptotes at y equal to 0. I will have a 1, then I will have a 2, and a 2 and a 4. So approaching to the, it's going to be like this. Sorry, the 2, I should put it here. Okay? I don't even need to give one more point. Okay, if you have a bigger space, yeah, certainly you can graph all 3 points and plus the horizontal asymptotes. So here you go. You get your y equal to 2 to the power of x. Now, in order to graph the log 2x, all you have to do is follow this. So when I have a 0 and a 1, so it's right here, okay? And I know that I will have my vertical asymptotes at x equal to 0. So I know that the tails is going to approach to the vertical asymptotes. And if I have a 1, sorry, so what I have here is a 1 and a 0 and a 2 and a 1, okay, and then a 4 will be a 2. So I know that my curve, my log function is going to be like this, okay, crossing the x-intercept at 1, 0. If you get a 2, then you go into a 1, so somewhere here. And if you get a 4, you get a 2 somewhere there. Okay? Don't forget about the arrow, but you know that your graph is approaching to the vertical asymptote like this. Okay? So this one is going to be your y equal to log 2x. Okay? So this is going to be the example number 3. So now you have some ideas how to get the key points for the log functions. We always start by going back to the exponential functions, okay? So sometimes we call this as this is going to be the parents functions, or you go back to your parents before you get your actual points here, okay? Now, when it comes to the transformations, that's the part that you need to pay attention to it. So the transformations of a log functions will be the same thing, similar to what we have done, the transformations of any other type of a functions. So we start with the f of x, okay, with the a, vertical stretch factors, times, if this is a log functions and you have a log, we don't know the base until we actually get the questions. But after the log, you will have a brackets of a k, horizontal stretch factors, bracket. So this value always need to be factored it out. Okay, if this is not factored it out, then you make sure you factored it so that with the brackets, x minus the d, so the d will be the horizontal translation, moving left or right, okay, and close the bracket plus the c. Whatever that you add after that c value is going to be the vertical translations moving up or down, okay? So AKDC is exactly the same as what we do with the other type of functions. But the only thing we have to make sure that you understand, keep in your mind that this brackets here, after the log, whatever the base is, okay, this bracket here always have to be positive, okay? Why? I hope everybody still remember one of the fact that we talk about it. If you have a log of some base, okay, but this is negative, okay, so that means this one has no solutions. Why? Because when you're taking the base to the exponents of a, it's not possible to get a negative answer here. Okay, because the base itself has to be greater than 1, positive. Okay, so the only variation or the only variable that you can turn into a negative is the a. But if the a is part of the exponents, then you cannot get a negative answer. No way. A negative exponents law already said that you always get a positive answer here, regardless what the a is. If the a is a negative 5, then you just have a 1 over b to the 5. Okay, so that's why it's important for you to realize that, you know, whatever that you ended up beside the log, that number has to be positive. If you ended up with a negative, that means that it's impossible to graph or it's impossible to evaluate. Okay, and also in the exponential form, in the exponential, y is equal to the, let me just put it over here. If in the exponential form, y is equal to b to the x, and we always have a horizontal asymptote at y equal to 0. But because this one is the inverse of that one, of the exponential, so therefore, in the exponential form, the c will tell us that where the horizontal asymptote is. Okay, in general, maybe I shouldn't say this is a y equal to 0, but this is a y equal to c. So in the exponential functions with the transformations, the c will give you or will tell us, well, where the horizontal asymptote is happening. But since the log function is the inverse of the exponential, so instead of having the horizontal asymptote, now we have the vertical asymptote. And where will the vertical asymptotes will give you the indications from the equation, and that will be the d. So it's not the c like in the exponential, okay, but in the log functions is the d that tell us where the vertical asymptote is happening. So the x equal to d will be the equation of the vertical asymptotes. So this is very, very important, because if you remember what we did before with the graph, the tails, one side of the tails of the log function is approaching to the vertical asymptotes. Okay, so just like in the exponential, where the one of the tails is approaching to the horizontal asymptotes. Okay, so this basically is the general form of it, and I just want to remind everybody about this mapping root. So again, any points from the original functions x comma y, after all the transformations, the k, the d, the a, the c, okay, you know how the k and the d will affect the x. So you take 1 over the k times the x plus the d. That will give you a new x coordinates. And when you take the a times the y, okay, and plus the c, you get the new y coordinates. So this is the mapping rules that we always follow. So we will be doing the same thing, okay? So now let's look at here. And this is the example that I want to show you, that this is going to be a complete, like the kind of log questions that you will be getting for graphing, that first you're getting a y equal to 2 times the log, okay, no number indicate, then the base must be 10, brackets 3 times the x minus 2. So now, very quickly, I want to show you that you have to identify the a, the k, the d, and the c. When there's no c, that means the c is equal to 0. So now I know that my a is equal to 2, the k is equal to 3 positive, and the d is equal to positive 2 because it shows negative before, okay? If the d is a negative, then you will see a plus sign here, okay? Same thing as the quadratic or the other one. And c, when you don't see anything, so c is equal to 0. So this is what you have in terms of transformation. But before we start to create the table values, and remember how easy that if we can get everything back into the exponential form, okay? But how can we get this into an exponential form? So there are one more steps in between. So with this one, the log equations with all the transformation. Now, I would call the parents functions of this one, the parents functions of this one. What would the parents functions of this one? Well, if this one has the base of 10, okay, then I would say the parents functions of this functions will be just a y equal to log x. Okay, so without any of the transformation, so this given log equations has a parents functions in log form, okay, log x, okay. Well, why log x? Well, because this one has no number beside, that means the base must be 10, so same as this one. So I'll call this as the parents of this one. But the because I cannot get the table values in this form easily, so that's why I need to go back to the grandparents functions. I call this grandparents because I need to go back to the a step further so that I can get my key points easily, okay? So the exponential form of the log x will be a y equal to 10 to the power of x. Because this one has no number, then you know that this is going to be in the base 10. So in the base 10, in the exponential form, it will be y equal to 10 to the power of x, okay? So from the given equation in log form, I go back to the parents functions of the log form, which is also a log equations, but without all the transformation. So I'm just giving myself a y equal to log x. And then go further step, okay? Go one more step, okay? So from a parents to a grandparents function, and the grandparent function is always referring to the exponential form of it, okay? The exponential form of the parents, okay? So it would becomes a y equal to 10 to the power of x. Now, so when it comes to the y equal to 10 to the x, then it's a lot easier for us to create this table value. So when I have a y equal to 10 to the x, then I know that if I give myself a 0, I get a 1, I get a 1, I get a 10. If I put in a 2, I get 100, okay? But because this is an exponential, I know that I have a horizontal asymptotes at y equal to 0. But this is not important anymore because now with the transformation, I already know what my vertical asymptote is going to be, okay? So you might not even need to write this, okay? But I'm just reminding everybody again that exponential form, you know, you always have the horizontal asymptotes at y equal to 0. Now, for the parents functions, I know that the parent function is the inverse of that, right? So the parents function is going to be the log x here. So what I have to do is I just interchange the x and the y. So 1 is 0, and 10, and a 1, and 100 here, and a 2, okay? I don't have to worry about the vertical asymptotes yet because this is not the graph that this is not going to be the final product of a graph, right? We are going to graph something that with the transformations on it. Okay, now, once I have all of this, then I'm going to give myself the table values for the function that I'm asking to graph. But this function here, I have the a that's 2, k is 3, and d is a 2, and the c is equal to 0. So right away, from this one here, I know that my vertical asymptotes is the C, right? I already, sorry, not the C. I'm making this, it's going to be the D. Okay, this is going to be my vertical asymptote. So is x equal to 2. Okay, and for the same x, 1 here, okay, for the same 1, 1, and a 0, I'm going to repeat what I have over here. Okay, maybe I'm not going to do the last one because this one is going to getting very big. But what I want to show you is that I'm going to multiply the A in the Y column, and I'm going to add the C, but there's no C, so I'm adding 0. So I'm just multiply the 2, that's it, because there's no C. And for the x coordinates, I'm going to multiply the 1 over k. So I'm going to multiply the x column with 1 over 3. And then I'm going to add the d, so plus 2. So I'm going to do the same thing here, plus 2. So I'm going to get a new x coordinates. So 1 times 1/3 plus the 2, so it's a 2 and a 1/3. So 10 times 1/3 will give you a 10 over 3, so plus 2, so it's 2, 10 over 3, approximately. You can get it from the calculator, okay? You can get the calculator, and you're going to, on the graph, you can kind of slowly, well, first of all, I'm going to make sure I have my vertical asymptotes drawn with a broken line. So I can say that this is my VA. X is equal to 2. Okay, and so the first point here, I have a 2 and 1/3, so it's a little bit over. So this is a 3, 2 and a 1/3, and it's going to be 0. So that means I'm going to have something x-intercept very close to the 2. Okay, 1/3. And I'm going to have a 2 and a 10 over 3. So this will be approximately equal to, if you work it out, as 6 plus, so 16. If you turn this into improper and then turn it into, it's going to be a 2 point something, 2 point, well, somewhere here, 3, 6, so it's a 16, like a 16 over 3. So approximately it's going to be, sorry, this is not the right way of calculating. Sorry, forget about that 16 over 3. But if you think about 10 divided by 3 and 3 point plus the 2, you're going to get 5.3 something, okay? So that means 4 and a 5, and you're going to get 2. So 1 and a 2 approximately here, okay? So this is a 5. 10 divided by 3, yeah. So this is going to be approximately equal to not 2 point something. This whole thing will give you approximately 5 point something, 5.33 something, okay? So it's going to be somewhere here. So I know that my graph is going to be something like coming from here, crossing this, and approaching to the vertical asymptotes. Okay, done. So this will be the graph. This will be the graph of the 2 times log 3 bracket x minus 2, because that will be after you stretch with the factors of vertical stretch by factors of 2, horizontal stretch by factors of 1 over 3, and then move it 2 units to the right. So that basically is what this graph is going to be look like. Okay?